Are you interested in satellite communications? If so, today we'll be reviewing each and every one of the L-band satellite antennas that I currently use for my day-to-day software-defined radio activity. Many of the satellites we'll be looking at today revolve around Inmarsat, Iridium, GOES, and even some of the low Earth orbiting L-band payloads such as the NOAA Constellation. If you're interested in software-defined radio and radio communications in general, be sure to smash that subscribe button and hit the bell icon so you don't miss any future videos. The first antenna I'd like to show you today is Inmarsat's Satlink antenna. This particular antenna would be placed on a mast on a ship, and it's made to keep a steady eye on a given Inmarsat satellite, so that way when the ship moves up and down and left and right, the antenna is able to stay locked on to the chosen satellite, ensuring that you have communications throughout your travel. In my case, I'd like to modify this particular antenna so that I can gain control over the servos using something like an Arduino or a Raspberry Pi, and then control this using software called gPredict. In this way, I'm hoping to mount the antenna in a stationary position and then lock on to low Earth orbiting satellites that happen to have L-band payloads, such as the NOAA satellites for their SARSAT downlink. The next antenna I'd like to show you today is a prime focus grid antenna. This one, I believe, was tuned for about 1.9 gigahertz, but you can also use the 2.4 gigahertz Wi-Fi grid dishes, and by moving the focal point of the antenna at the end of the boom, you can better tune in various signals, such as those in the L-band at about 1.5 gigahertz. Primarily, radio and weather reception hobbyists have been using these grid dish style antennas for listening in to the GOES 16 and GOES 17 HRIT signals broadcast at about 1.694 gigahertz. These signals contain full disk images of the Earth, among other bits of information, which have been incredibly valuable. Keeping in mind that such antennas do not provide their own LNA, or low noise amplifier. This means that you'll have to get one of your own in order to properly see these signals. For GOES, I tend to use the New Relic Sawbird because it not only contains a low noise amplifier, but a nice saw filter to ensure that only the signals you're looking for are able to be received. We'll also find that the GOES satellite has a transponder at 1.68 gigahertz, which contains DCP data. This is data from USGS gauging stations that I spoke about in a previous video, link in the description below if you're interested in that. You will find that a grid dish like this is actually pretty flexible. By simply moving our satellite dish slightly off to the right, I can go from the GOES satellite over to the Inmarsat satellite. And so in this case, we can now use the same satellite dish for our receive of the Inmarsat satellite. Now, in this case, you may recall that I had a New Relic Sawbird, which had a filter specifically for the GOES signals. In this case, I'm using an LNA for all. This is a more generalized low-noise amplifier that does not contain any filtering. Because of this, it is perfect for using for Inmarsat, Iridium, or any number of other L-band services because I don't have to worry about it blocking out certain frequency ranges. Speaking of the Iridium satellite constellation, here you can see my Iridium antenna. It is housed inside a piece of PVC along with an N connection at the bottom for the antenna. Within this, I'm using a New Relic Sawbird. You'll find that they make these in various revisions for different satellites. This particular one tuned specifically for Iridium. For the antenna, I'm actually using a GPS QFH antenna for a weather sonde, essentially a tracking device used for locating released weather balloons in our atmosphere. This particular model uses a QFH antenna instead of a piece of ceramic. QFH antennas are somewhat difficult to build, and it gets much harder once you start going up in frequency. So I've taken this GPS QFH antenna, removed it from the existing circuit board, soldered an SMA connection at the bottom, and then attached it directly to my New Relic Sawbird before mounting it in its PVC housing. The QFH antenna is nice for Iridium reception because it is omnidirectional in nature, and it makes it a lot easier to receive signals in a low Earth orbit where the satellites are constantly moving. Unfortunately, you'll see here that I don't have a permanent location to mount my antenna and was just holding it up for this recording, and that's because for some reason I have a bit of terrestrial interference that I just can't seem to shake. Iridium, however, holds a lot of interesting information such as text messages, voice calls, and numerous other services that are provided through the satellite if you have the tools to decode them. From here, let's take a look back at Inmarsat. Here you'll find a professional series Inmarsat antenna. This was by Thrain, if I'm pronouncing that correctly, and is set up for Inmarsat reception as well as transmission, assuming you're licensed for that purpose. To make my connection to the SDR, you can see that we have an SMA connection going into a barrel adapter here, and this goes to a 12-volt power injector used for an amplifier for traditional cable television. That goes through some RG6 that I was able to cobble together from some old satellite equipment that I had laying around, and then that goes to an adapter with a TNC connector to make the final connection to the panel antenna. So you may be wondering why we're using a 12-volt power injector on this particular panel antenna. Well, it just so happens that this particular antenna has its own built-in low-noise amplifier, and just so happens to run on 12 volts DC instead of the usual 4.5 to 5 volts DC that you may be familiar with using a traditional bias T on your software-defined radio. So rather than using the bias built into the SDR, we're using the 12-volt power injector instead. The reception of Immersed is quite strong and more than enough to decode all of the information that we may be able to find on the Inmarsat satellite service using the various software applications that are available, such as Gyro. And of course, I've done a video on Inmarsat in the past. You can find a link to that video in the description as well. I also went ahead and pointed this panel antenna over at GOES to see if I could pull in that signal. Unfortunately, I wasn't able to see the GOES HRIT signal, but with an added LNA, I was able to pull in some of the DCP data, although it was still quite weak. Here we have a set of smaller patch antennas. This first one here is the OuterNet L-band patch antenna back before they moved their services to the KU band. It's printed on some PCB with an SMA connector and also has a built-in LNA and SAW filter just for the Inmarsat signals. On the right we have a double-sided copper-clad PCB that I've placed my own ceramic patch onto and very dirtily soldered an SMA to the back because the panel mount SMAs I was waiting for have not yet arrived. Eventually, I would like to make this a gap patch antenna, but because I had a ceramic receiver on hand, I thought I'd give it a try. However, to use my particular antenna, I'm going to need a third-party LNA, such as those provided by New Relic. First, we'll take a look at the patch from the OuterNet project, and you'll see because of how strong Inmarsat signals are, I can literally just sit this patch down and use the SMA connection itself to hold the antenna at the right inclination so that I'm roughly hitting the satellite. Because this antenna is built specifically for the Inmarsat satellite service, you'll find that it actually does a very good job at pulling these signals in with next to no effort. From here we'll look at my DIY work in progress patch antenna, and you'll see that I'm feeding this using an LNA for all as my low noise amplifier. It does an okay job at pulling in some Inmarsat signals, and while it's not the most powerful thing in the world, it is good enough to get a decode on some of the lower bandwidth signals. And while I would generally never recommend it because it will definitely increase your noise floor, I did go ahead and place a second LNA for all and a bias T power injector in between the first LNA and the software-defined radio, in this case the AirSpy R2. We can see that it does give me some somewhat increased gain, but of course, like I said, we are going to have a noisier noise floor level, which is going to cause some problems on some signals. And while not explicitly for L-band, I also wanted to show you my V-dipole that I use for 137 MHz APT on the NOAA satellites. Unfortunately, I don't have any good signal samples to show you for this one because, as you can see, the weather has actually tilted this antenna at an angle at which I'm not going to be able to properly listen in to a NOAA satellite. But I still wanted to go ahead and show you kind of what it looks like and how I have it set up on my mast. You'll also notice my 2m/440 J-pole antenna, as well as my HF dipole antenna that I use for 20 and 40 meters. I hope you enjoyed this video. If you'd like to support the channel, please be sure to like this video as well as subscribe. And if you happen to join Patreon, you'll get early access to all of my content. We'll see you in the next one.